Hey everybody, welcome back. Welcome to Unit 6. Today we're going to be covering Lesson 2, which covers Charles' Law. So in the last video, we talked about Boyle's Law and the relationship between pressure and volume. And just to recap, that was an inverse relationship. So if pressure went up, volume went down. If pressure went down, volume went up. They do opposite things. Today, though, we're going to talk about Charles' Law, and that's the relationship between temperature and volume in gases. So this dude, his name is Jacques Charles, a French chemist and physicist, and he is known for studying the effect of temperature and volume on a gas at constant pressure. So Boyle's law kept temperature constant. Charles is like, yo, we're going to keep pressure constant and just look at volume and temperature. So that is what he's known for, but let's get into this in more detail. So Charles' law says that the volume of a given massive gas varies directly, so keyword here is directly, with the absolute temperature of that gas while pressure is held constant. So what does that mean? It means that there is a direct relationship between temperature and volume. So what that means is that if volume goes up, temperature goes up, or if volume goes down, temperature goes down. So whatever one thing does, the other thing does the exact same thing. So it's categorized by that, straight line going up. One goes up, the other does the exact same thing. So goes up, goes up, goes down, goes down. Now, these two GIFs kind of show this in action. So let's break this down, because this is really why stuff works the way it does. So if you look at the ice is cold, ice cools stuff down. So you have this balloon full of gas particles over the ice. And so you notice the ice getting smaller. Now, when things get cooler, so we need to introduce something called average kinetic energy. So average kinetic energy. I'm going to abbreviate it throughout the video as AKE. And so basically it's the movement of the particles. So particles either move slower or they move quicker. So the way temperature is involved in this, average kinetic energy and temperature kind of go hand in hand. So if, for example, the temperature goes up, so temperature is increasing, make that better up, then the average kinetic energy is also increasing. So that means the particles, particles move faster. So the higher the average kinetic energy, the more they're moving, the faster they're moving. Kinetic energy is really the energy of movement. So fast things tend to move really, really quickly. But oppositely, if you decrease that temperature, cold things move slower. So average kinetic energy would decrease, and the particles move slower. So knowing this, and we'll cover this in the next video as well for the next law, that key relationship is important. So temperature and average kinetic energy go hand in hand. So in this balloon over the ice example, the ice is cooling down the gas in the balloon. Now look, there's no gas coming in, there's no gas leaving. Whatever you have is there. So when the gas inside the balloon is being cooled, the temperature is going down. So the particles are moving slower and slower and slower until the average kinetic energy decreases. So with these slower moving particles, they bump into the walls of the balloon a lot less frequently. So if they're not bumping against the side of the walls of the balloon kind of gets smaller and the volume decreases. Because what keeps the balloon inflated is these gas particles, molecules bumping against it. But if they're moving slower and they're not bumping against the wall as much, the balloon looks like it's going to deflate a little bit. Conversely, though, if we look at it being heated, the candle is warming up all of the gas particles in the balloon. So with the heated up and the increase of the temperature, now the average kinetic energy is moving quicker. The particles, the hotter they get, the faster they move. So now, if the particles are moving really, really fast, they're bumping into each other a lot more. There's more collisions, there's more bumping, there's more everything. So with this increased average kinetic energy, because of the increased temperature, the particles are bumping against the side of the balloon a lot more, and that's what causes the balloon to expand and that volume to increase. So that's that direct relationship between volume and temperature. One goes up, the other goes up. If one goes down, the other goes down as well. Okay, so one of the other important key things to point out before we jump into calculations is something called Kelvin. So whenever we talk about or do gas law equations, we have to use the temperature unit Kelvin. Now that may be new for you, and you already know that, but that is super important. And what Kelvin does, it's another temperature scale, but at 0 degrees, at 0 Kelvin, we don't say degrees, it's at 0 Kelvin. That's when particle movement stops completely. So all particles have some sort of, motion. Gas particles are moving back and forth really, really quickly. Liquids, they're slowed down a bit. They kind of glide past each other. And you might think that solids are completely, they don't move, but there actually is some kind of vibration between all the particles. You can't see it, you can't feel it, but those particles are vibrating. But at absolute zero, so 0 Kelvin, that is when all particles, in theory, stop moving. So the 0 Kelvin is theoretical. At this point, in making this video, I have not yet heard of them getting to absolute zero. They've gotten close to it, but not actually zero. But that is when all particles stop moving. And just to kind of give you an idea as to how cold that is, here's Kelvin. It's negative 273 degrees Celsius. And that scale means very little to me, honestly. And then you have negative 459 degrees Fahrenheit. Well, that is so cold. Just think of it, freezing is 32 degrees Fahrenheit. So that is really, really, really cold. So before we jump into the actual Charles law equation, we should probably cover the Kelvin conversion. So this formula right here to convert between Celsius and Kelvin is given to you on the reference table, the back of the reference table, table T. And so sometimes questions will give you the temperature in Kelvin, sometimes they give it to you in Celsius. Your job is to remember these 9 letters, use Kelvin. So whenever you get any gas law related homework, classwork, test, quiz, project, anything, those 9 letters need to be on your page. Use Kelvin. So this is a very easy conversion. If you're given Celsius and you have to convert to Kelvin, all you have to do is add 273. So if we're going to take 15 degrees Celsius, convert it to Kelvin, add 273, and you get 288K. That's it. So for this one, what would be 100 degrees Celsius in Kelvin? So again, all you're going to do is add that 273, and you get 373K. That's it. Now, if you do a little bit of equation manipulation, you can solve for C, which is really just Kelvin, whatever you're given in Kelvin, minus 273. So if you're given, let's say, 300 Kelvin, you want to convert that to Celsius, minus 273, you get 27 degrees Celsius. Now try this one. What is 275K in Celsius? So again, you're minusing 273, and you get 2 degrees Celsius. That's it. So for Kelvin, you don't add the degree sign, it's just K for Kelvin. Okay, and so here is, another kind of infographic is, I guess, the okay word to use, showing the comparison between these 3 temperature units. There are 2 other temperature units that exist that I know of at this point in time. I just know they exist. That's pretty much it. But Kelvin is where we are at right now. Okay, so before we jump into the equation, Charles' law is something you see in everyday life. So here are some examples. I'll walk you through it really quickly. So if you've ever blown up some kind of inflatable for a pool, it's normally a hot summer day, you blow it up, it seems, good to go. Throw it in the water, get in it, use it, and you're like, wait, did I break it? Why is it deflated a little bit? So what happened is that when you blew it up in the outside of the pool, the air is a lot warmer. When you put it in the pool, the air inside the inflatable cools down, particles move slower, less collisions with the wall, the volume actually decreases a little bit. So no, your floaty isn't broken, it's just cold. If we're looking about baking bread, so if you've ever made bread before, you know, and you want the bread to rise, you use yeast, you let it sit. Another word is prove, you let it rise. So basically, yeast feeds on some of the sugar in the dough and produces gas. Now that's what it's supposed to do. But when you let the bread rise or you let the bread prove, you put it in a kind of warm environment, not oven warm, but just a little bit warm. So all those gas bubbles that came out of the yeast are able to expand. Because remember, if you're increasing the temperature, the volume of those gas bubbles is able to increase. And actually gives you these very puffy, light breads. Definition of Charles' law. Increased temperature, increased volume. So you get these little air pockets in the bread. Hot air balloons is also an example of Charles' law. You know, without the hot air, the balloon will not fill up, and the hot air is also less dense. So density is involved in there as well, but Charles' law is the lay of the land there. Okay, so we're almost ready to jump into an equation. So here it is, V1 over T1 equals V2 over T2. Again, just like Boyle's law, it's that before and after situation. So they'll give you 3 out of the 4 variables. Your job is to figure out the 4th one. So again, you need to use these 9 letters on top of your page. Sometimes they'll give it to you in Kelvin, the temperature, sometimes you have to convert it, but you need to use Kelvin. Another thing before we jump into the same slide from last video, STP means something. So for every unit except for gases, which is where we're at now, STP means something. So if you're given 2 out of those 4 variables, you're like, what do? I don't have enough information. You do. It says STP. And so that means you need to talk about that and look at that part of the table. Again, this comes right from the reference table. Now again, if we're talking about gases, you need to use Kelvin. So we are looking at 273K. So that is your standard temperature. So with that all being said, let's jump into this. So just like last time, we'll go through 3 questions. We'll make some predictions. We'll calculate it, and then we'll check ourselves. So number 1, it says in a cylinder with a movable piston contains a sample of gas having a volume of 6 liters at 293K and 1 atmosphere. What is the volume of the sample after the gas is heated to 303K while the pressure is held constant? So let's make it, first let's write down what we know and what we don't know. Oops, V1, T1, V2, T2. So we have 6 liters. We have 293K. So our unit is in Kelvin. We're good to go. We're looking for this, and then temperature's increasing to that. So our prediction, we know that temperature is going to increase. So, and we know it's going to be a direct relationship. So what do you think happens to the volume? So you should have said volume increases. So that's what that direct relationship says. So let's see if our prediction is right. Let's plug in our numbers. 6 over 293 equals V2 over 303. Do some nice cross multiplication. Move down here, grab a different color. We get 6 times 303 equals 293 times V2. Divided by 293, divided by 293, which is 1818 over 293, which gives you 6.2 liters. Now, we predicted that volume is going to increase, and we started with 6.0, we're ending with 6.2. So does our calculated answer match our prediction and make sense? The answer is yes. So again, these questions aren't the most difficult of things if you're organized with your work and write down your knowns and unknowns. Okay, let's jump into this one. A gas occupies 1 liter at standard temperature. What is the volume at 330 degrees Celsius? So there's a lot going on here. We have V1, T1, V2, T2. We have 1 liter. And then our temperature 2, we're looking for this, is 330 degrees Celsius. Now, can we use this unit of temperature? Answer is no. We must use Kelvin. So we got to convert this to Kelvin. So what we need to do is add 273. So you get 603. Okay, so 603 is going to be K our T2. But now you're still like, I only have 2 of the variables. Where is the third one? At standard temperature. So if we go back, remember that's 273K. So standard temperature, STP, that means something, 273K. So now you have all that you need to set this up. So if you plug it in, you get 1 over 273 equals V2 over 603. Do some cross multiplication. 603 times 1 equals 273 times V2. Divided by 273, divided by 273, you get 603 over 273, which gives you 2.21 liters. Okay, just realized we forgot our prediction, but let's check it. We know there's the direct relationship, so if volume goes up, temperature goes up, or if one goes down, the other goes down. So temperature was increasing, so the volume should have increased, and did it? It did. We went from 1 to 2.2. That is an increase in volume, so yes, our answer does make sense. Okay, so let's jump into one last question. H2 gas occupies a volume of 400 milliliters at 27 degrees Celsius. Find the volume it will occupy if the temperature is increased to 57 degrees Celsius at constant pressure. Okay, so we have V1, T1, V2, T2. 400 mils is our volume 1. Temperature 1 is 27 degrees Celsius. We're finding this, and we're ending at 57 degrees Celsius. Now, can we use these temperatures as is? The answer is no. We must convert to Kelvin. So add 273 to both. You get 300K and 330K. So now we have everything we need. We're good to go. Let's plug it in. 400 is our V1 over 300. Remember, we just converted that to Kelvin. So use Kelvin equals V2 times 300. Hold on, my bad. Okay, starting over. We have V1, which is 400, over T1, which is 300, equals V2 over T2, which is 330K. Okay, my bad. So then you do this, and you get 400 times 330 equals 300 times V2. Divide both sides by 300. You get 132,000 over 300. That gives you 440, and our unit is milliliters, and that is it. So again, really the most important part right here is remember you're using Kelvin. Keep track of your numbers, and these questions aren't the most difficult of things, as long as you stay organized. So that's pretty much it for this. Next video, we're going to go over Gay-Lussac's law, and that's the relationship between temperature and pressure. So that last grouping of those 3 variables. So that being said, that is it. Have a wonderful day.